All right, we're going to get started. Welcome everyone to PowerPanel's educational webinar. We are your thermal energy headquarter. That is our new tagline. And today we want to use this opportunity to explain to you why that is the case. So why is PowerPanel your thermal energy headquarter? There's really two main drivers to that rationale. Whoops, what happened to my thing here? I lost the slide. Oh no. So why are we the thermal energy headquarter? There's really two main elements here. Oh, here it is. Sorry, I have it in the wrong order. The first one is thermal storage. Thermal storage allows you to bank energy when it is cheaper to do so and use it when it is needed. So in the chart below here, you can see how in some markets, there is a clear fluctuation of energy usage throughout the day. There's the morning peak when everybody's getting ready, taking their breakfast, cooking stuff, taking showers. And then there's an evening peak when people come home, they go on their televisions and so forth. And in between and at night, there's a valley. And the cost to provide electricity during those peaks is higher because the utilities have to bring additional resources online. What's on the very bottom, the yellow, is called the baseline. And then the different tiers are more expensive and more expensive options. And they only bring online the most expensive options when really necessary. And then, of course, as the utility has a higher cost, they want to get paid for that. So many utilities are introducing time of use rates, where if you use electricity in those peaks, you're going to pay significantly more than if you're using electricity in the off peaks, in the valleys, or at night. So if you are turning on your shower and you don't have any kind of thermal storage, your hot water system has to draw on electricity right there and then, and you have to pay whatever rate the utility is charging you. But if you have a thermal storage device, you can essentially charge it up at night like you would do with a battery, and then you can use that lower cost energy when you need it or when your guests need it during those peak periods. The second driver is thermal energy capture. The battery or the thermal storage solution does not really care where the energy comes from. You could charge it up with just regular electricity provided by the utility, or you could capture lower cost, cheaper, or even waste sources of energy. And there's three we're going to talk about. Solar. The sun is providing us with an ample amount of energy, and many people have used it to turn it into electricity, but we can also turn it into hot water. There is ambient energy, the temperature that is in the environment, and we have ways of capturing that through heat pumps. And then there is waste energy. That's really my favorite, energy that you're already paying for, that is going to waste today, and we have a chance to reclaim that and convert it into hot water. And our understanding of these dynamics and our solutions that provide you with these values make us your thermal energy headquarters. So how much exactly can you save? It varies client by client, but let's start at the very top. If you are using electricity today to heat your water, and you are in a market with different rates for peak and off-peak usage, and then there's another component called demand charges, where the utility does not only charge you for the amount of electricity that you have consumed, but they're also looking at your profile. And over a 30-day period, they're going to find the moment in which you had the highest of all electricity demands within your business or within your home. And they're going to call that your peak demand. And for that, they're going to charge you a demand charge. So we can help you avoid demand charges or reduce the demand charges, move your usage from peak to off-peak, and we can move you from straight electricity to cheaper sources of energy. And in a best case scenario, combining these three levers, you could save up to 90% of your current cost for hot water. One level below, if you're not in a market that charges these rates, you could, but you're using electricity today and you're in a climate that is consistently warm, such as Puerto Rico, the Caribbean, Florida, California, Hawaii, we can still help you save up to 70% of the energy. And that is where we will talk about the heat pump. The heat pump operates on electricity, but it basically takes one input of electricity, and then it draws in energy from the environment, from the surrounding air, the warmth of the air, and converts that into thermal energy. And there is a ratio called coefficient of power. So if the heat pump can create 4 units of output to 1 unit of input, that's called a COP of 4. And you can typically, heat pumps get up to 3.5, maybe under ideal circumstances up to 4. The Caribbean is an example of that. So that's the second best use case. On the other end of the spectrum, so then there's a wide range in between of savings potential. On the other end, we cannot help every client. There are some situations where clients have access to very cheap natural gas for heating their water. And so even if we install our equipment and we run it, it may not pencil out from a business case. And we'll look at some examples of that later on. Now, we can claim all of this, but at the end of the day, the question is, what do the experts say? And the experts have referred to PowerPanel as really one of the up-and-coming solutions, referring to the great energy retention of our thermal battery, the simplicity, the safety, easy to manage hot water solution. So it's not that we're the only ones making this claim. Industry-leading magazines have validated that this claim is justified. That, of course, begs the question, so how exactly does it work? And in part 1, we're going to talk about the storage element. And here I'm going to introduce a very important person, and that is Garth Schultz. Garth is the one who invented this technology. Garth, if you could maybe explain to us the fundamental principle of how, and we'll focus on the tank for a moment, how you've designed this tank, how this came about, and what some of the sort of operating principles are here. Do we have Garth on the call?
Mute myself. Hey, how are you guys doing?
Good.
So tank came about because someone stiffed me on delivering a tank. Thermal storage. I had set up PVT modules. I was incubated in downtown Detroit at a site called Next Energy. Had some preliminary PVT modules that in design needed a thermal storage device. Contracted with someone, and it never ever showed up. So had a small lab space and had to move in something in order to store water. And so it just gave rise to, I got a doorway only so wide and a tank that I wanted so big, and just kind of went back and just dreamt up. I said, this is what this thing wants to be like. So it's segmented. So if in an assembly diagram, if you could, I needed to get a device that you could go and walk in anywhere and set up easily. Now, there have been a lot of, over the years, some design improvements, but materials externally on the tank hoop, liner materials, but the basic principle of using expanded polypropylene foam, non-degrading in any and most environments, and then highly retains energy very well because there's not a lot of what you call gaps in order to have thermal energy, hot or cold, escape. So the design impetus was, how can I get this into a small space, get it set up, and make it so that it's easy for the installation crew to do. And there's other benefits that we'll probably talk about as part of that, but it basically came about as a need.
All right. Now, one of the key principles of sort of, we called it a tank, right? But we are moving away and calling it really a thermal storage solution or even a thermal storage battery, is the idea of a working fluid. Can you explain a little bit more the logic behind that and how it actually works?
Sure. Working fluid is, it becomes a one-time fill. So if you're dealing with water, water could be of various qualities. So as that moves through a typical hot water heating system, you're always seeing a fresh load of minerals, of whatever substances in the water that can degrade the interior or the tank itself. So that's why if you watch any videos, or you probably have practical experience, you crack a hot water heater open and you get this white sludge, or you see ones that are cut apart. It's that fresh mineral load coming in all the time. We're a little bit different because we fill up the tank with and water's our working fluid for all environments, and that's a one-time fill. So the mineral load that's in there out of that one single, out of a tap load, never ever deposits once. Might see a little film on the liner material, but you don't have that constant build of having a fresh load of water through there. So we take that working fluid, put it through the device. An example in front of you, it's an air to liquid heat pump, and it just continues to build that thermal potential in that tank to your desired delivery levels. Then within that tank, we put an immersive heat exchanger assembly. The one pictured, it's an all plastic one, so that you can once again go into variable water environments and still have success that this thing isn't going to degrade. We also have a stainless steel models available as well, and we can play to the flavor of what you as the client or customer wants to take away in terms of a heat exchanger design. So we get plastic, steel. We're kind of agnostic to that, but what we bring there is that great base to store energy, and very effectively.
All right. I want to go into a couple of examples. So we've seen in the Caribbean that many hotels make their own water through reverse osmosis, and that water tends to be very aggressive. Can you explain how the design of the tank and the design of the heat exchanger in particular can handle that aggressive water?
Yeah. So that aggressive water never ever sees the interior of our tank. It sees the interior of the heat exchanger, and in terms of the design presented in front of you, the one in the upper right-hand corner, it's a polymeric. It's an all nylon design. So that mineral load is not going to grab onto metal ions, cause rust or corrosion within the system. So that's how we avoid, in an aggressive water environment, the system from going null and void after a few years.
Another example we've heard is that when people are on utility water, after power outages, when the pumps come back online, there is a lot of debris that is in that public utility water. Do we have any capability of protecting that heat exchanger from being exposed to that debris? Are there any filters that could be built into the system?
Oh, certainly. In fact, we've specified in at Windward Passage Hotel, because that is a common occurrence, that the water utility goes down, and when those pipes are evacuated and or put back into service, there's a certain amount of rust and debris that comes through, so we can specify a filter set. At Windward Passage is an all mechanical screen. I think we specified that for you, Carla, as part of the roll-up into your proposed site, and it's down at I think a 5 micron mesh filter, but it self-cleans. Once it says I'm clogged, it ends up going through a cycle in order to self-clean. So you're not having to constantly swap filters out.
All right. So we've talked a lot about the amount of money we can save clients on their hot water needs, but the tank is also capable of storing cold energy. Can you give an example, Garth, of how that cold energy can be used by our clients?
Certainly. So same air to liquid heat pump that's shown in the schematic. And instead of operating to pull energy from the atmosphere and put it to work as domestic hot water, just as a normal air conditioning system, chiller, we pull from the interior of the building and then out towards the atmosphere to expel it. But those systems, they want buffering or storage between them, because otherwise there's a phenomenon called short cycling. That means you might have a demand on the hydronic system or on the HVAC or air handler system that says, oh, deliver me cold air. And the heat pump goes, well, I don't have enough capacity in the system. And or the inverse happens. You have the chiller wanting to make chilled water, but there isn't a demand on the other side. So you put storage and buffering. It's like a good having a good capacitor in an electronic system. Once again, that analogy of energy storage, you can equate on an electric system, but in here it's a thermal matter. So those thermal capacitors or buffering, those are common in HVAC. It's just that, what we have in terms of how to get it deployed in at site and where you can locate it, inside, outside, we can bury the tank at grade, makes it very flexible for the HVAC system designer.
All right, excellent. You had mentioned earlier how the necessity to get a tank through a narrow doorway led you to this modular design. I was recently able to witness the assembly of a tank in Puerto Rico, and it was really amazing how people who had never done this before were able to do it in a few minutes. Can you talk about a couple of the advantages of this lightweight modular construction in terms of transportation, installation, moving it to other places?
I think that comes, right from, where the parts are produced. So we can fill up a 40-foot ISO container with 55 of those 350-gallon tanks, whereas if these were solid or unitary devices, you would end up being able to only ship, maybe up to 8 in a 40-foot container. So starting right from there, that there's an economy on movement. And then once you're at site, you're not having to block off a street. Let's say this tank wanted to be up on a rooftop. So no cranes involved. You can take the individual pieces up a common service elevator to rooftop and deploy them. So the most important thing is, it's labor, it's time at a site. So when the tank arrives, you can grab the parts and get them in place very quickly.
All right, excellent. We recently visited a hotel site together, and they had just witnessed the explosion of one of their water boilers. Too much pressure in the system. Our tank sort of prides itself on longevity. Can you go through a couple of the elements that contribute to that longevity? I think you've talked about the material selection earlier, but also this idea of pressurized versus unpressurized.
It is an unpressurized tank. The volume that's holding the energy is it's exposed to atmosphere, so it doesn't have that pressurized fault built into that system. The only thing that's pressurized in the system is the fluid within the heat exchanger set that you have within there. Now, starting from the outside, the outer skin that the tank is assembled of and the top lid assembly, that's a common roofing material. So you end up with a 25-30 year guarantee against the color loss, all the good things that on a proper TPO roofing system we've incorporated into this outer skin. So it's meant to be in an outside environment and exposed to sunlight. The next step in the EPP material, 100% recyclable. The steam chest environment that it's built in is meant so that if at the end of life, if this wanted to get reclaimed, it's 100% reclaimable. Interior liner, we can, typically we're storing hot water, and hot water is a working fluid in it. So we have a PVC liner, once again, 100% reclaimable, and meant for temperatures up to 90 degrees centigrade. But we can spec that liner material there if you have a wish and a want to store something, potable. We can do that as an aside. But all these elements gather together, and the little bits of fasteners and the little metal brackets to hold the lid assembly together, those are all once again 100% recyclable, and then they don't degrade in their working environment.
So we have not had one of these tanks out for 20 years, right? But if you had to estimate the life cycle, lifetime value of a tank like that compared with a typical water boiler, how would you compare the two?
Well, I look at this as an appreciating asset. So once installed, its value only goes up. Anything that's metal, that's you have a corrosion factor, it's a depreciating asset that eventually needs to come out of service. What you'll keep an eye on in terms when this is in service is the liner itself, but the materials and the construction, we've had them out in the field for a dozen years, if not more, and they just don't degrade because, once again, the liner is protected from any sunlight, by the construction of it, and it's a nicely tightly held assembly.
So when people compare the cost of this solution versus a traditional solution, they have to factor in that the traditional solution may have to be replaced 2 or 3 times over a course of 20 years, whereas this is a one-time investment. Is that a fair characterization?
Oh, correct. Yeah.
All right. Next, I want to talk a little bit about the controls. Obviously, if you want to take advantage of peak versus off-peak cycles, if you want to reduce the demand load at the right time to avoid those demand charges, you need to be able to have some smart controls. You need to know how your system is operating. And so, Garth, you've built this in to the system. Can you explain a little bit how these controls work?
Sure. First, I'll speak to the heat pump controls. Our heat pump expert, Josh Plasted. So he's working with a company to provide that control over a heat pump system that can schedule on and off times according to electrical demands and desires of the client as to when this device wants to come on. For us on the energy harvest side, we have our own embedded controller that is wirelessly connected to the internet, and that we monitor and program and can pick up data sets, historical data sets, so you can monitor trends and show performance of the system.
All right, excellent. We're going to switch over now from the storage to the energy, to the thermal energy capture. We've talked about one mechanism already, the heat pump, that takes one input of electricity and turns it into 3.5 to 4 outputs of thermal energy. But there are other mechanisms. I talked earlier about solar and waste energy. We're going to start with solar because that's another core invention that Garth has made. Typical PV solar cells really only capture electricity. And Garth, if you could sort of walk us through the logic of what you have built here and how it is possible that it can also generate hot water.
Thank you. The design impetus was to, maximize efficiency from the sun. At maximum, at our normal rate of the sun delivery at full sun is 1,000 watts per square meter. And as Oliver pointed out, typical solar cell can take away 20, and they come up a little percentage every year, but on a module basis, there may be a 23, 24% of sun capture. We, on the other hand, that sunlight that doesn't turn to electricity by striking in a photovoltaic cell it just turns to heat. So that becomes a valuable energy stream as long as the client can utilize it. So we've constructed a collector system based upon a simple drain back mechanism and an energy capture mechanism that allows us to build a complete system that 84% peak efficiency.
So what we're looking at here is your patented solution in the way the water cascades behind the solar cells. And explain a little bit how water and electricity in such close proximity, why is there no sort of danger in this system? How do you keep the two separated?
Sorry, Garth, just a clarification. You're saying 83% system efficiency versus, or module efficiency versus the 20% on a straight PV.
Yeah, a peak efficiency. Yeah. So last time we've had this thing tested, actually a client or a collaborator over in Israel, he took it to Standards Institute of Israel. We have our SRCC, it's like 76, 78. We've made some improvements since then. And they tested it almost 2 years ago. And they said, here's your peak efficiency of 84% out of the module. So it looks like a very, very good unglazed collector at peak, like a what do you want to call it, pool heater at its peak efficiency. But then since we're glazed, it goes out so that it performs like a good flat plate glazed collector. So everyone on the call, a really good flat plate glazed solar collector, they're often in the range of 75, 80% efficient. We just happen to combine in to make the PV element, because that gives the benefit to the customer to operate electrical components, but also that thermal component, so that their desires or their energy demands in their building are met as well.
All right, excellent. Now, you mentioned how there's different levels coming together here. So we maybe you could walk us through, and in that context, come back to my question of how can you have water and electricity in the same device and nothing bad happens?
Okay. So up in front of you, what we'll call the PV insert. So that's where we wet our solar cells onto. I got a little model in front of me. So 28 cells, HJT technology, but the absorber plate that we have them adhered to through a two-part silicone encapsulant, it's made from a hard coat anodized aluminum sheet. So water is going to be present on this side as it works its way down through the module, but on this side, where the electricity is generated, and we're separated by adhesive sealant that blocks off the water from getting onto the cell side. So they're entirely separate systems, but as you can imagine, sunlight comes in, impinges on the cell, turns some to electricity, 20%, and that goes out into the system, but the rest turns into heat, which is driven through this absorber plate into the water that's cascading on the back in order to capture and take away that heat energy. And to keep peeling it apart, the secret sauce on the module, it's the absorber. So this thing that has the little curious, we call them the 7s and J's, depending on how you look at them, and all of them end up with an adhesive bead on them, about 12 meters for this on this module that gets that the insert gets applied to. And in terms of design, the water goes down, any air trapped in the system works its way out for a complete wet out, so you don't end up hot spotting the cells. And it's a very efficient method in order to, by cooling the cells, ups that cell's efficiency, but then that energy is taken away in the thermal stream. And then the back, any kind of proper flat plate glazed collector, the bottom part of that assembly, it's a expanded polypropylene foam component that then is married onto the flow surface. And then in turn, either the PV insert comes in to comprise the assembly, and then not shown here, but we put a top glazing of glass, so it becomes a flat plate glazed collector. That means there's an insulating air gap between the cells and the glass itself.
All right, excellent. Thank you for that. So when it's all put together, it looks somewhat like what we see here on the right-hand side. How would a client determine how many of these individual modules or how many of these arrays are needed? How do we typically assess the energy need for a client?
Well, we'll go measure. One, you have estimates, so you have some standard data ASHRAE and others can produce. If you're in a dorm with a bunch of people, 13 gallons per user per day, and so you can do that energy calculation. If it's in circumstances where the client is not sure what their usage is, they know that they have generating devices, we can go in and measure that hot water amount. But knowing that energy requirement on what they want to heat their water to and the volume of usage, then we run it through a series of calculations in order to specify how many array sets that they would need at site. So what's in front of you right there, that 20 module array, that looks like 12.7 kilowatts of thermal power and 2.7 kilowatts worth of electrical power. Energy storage in underneath that array set, at 700 gallons. And at a 35 degrees C temperature differential, that looks like 108 kilowatt hours of stored energy. So effective capture plus effective storage.
Now, the sun is not equally kind to all geographies, right? Here in Wisconsin, we get more of it in the summer and less of it in the winter. Is your system adaptable to different geographies, different latitudes?
Oh, correct. Yeah, the module we designed for up here in the Midwest. So you got freezing, snowbound weather. Even the controls of the system, we can actively melt snow off the module and put it back into and make sure it's back into service in a wintertime environment. But the nature of the module is a drain back. That means any working fluid that's up in there, when the pump stops, when the control system says there's no more energy to gather because of cloud or time of day, then all that working fluid works its way back down into the tanks. And as those large thermal volumes, they maintain temperature for a long period of time, even in wintertime conditions.
All right. Now, your background is you are an automotive engineer, and in the automotive industry, you got to design things really well, otherwise you get
Sorry,
sued.
I'm just gonna.
Yes.
Just one question. Your maximum tank temperature was 140, right?
Tank the peak. Yeah, the tanks are rated to 90 degrees centigrade, so 200 Fahrenheit is what the max temperature. Collector temperatures, because you're playing that balance in a PVT system between electrical output, so that wants to be as cool as possible, and by taking away the energy produced, that you think, well, you're stagnating the module, that actually helps to cool that. But that balance that we kind of find is 55, 60 degrees C kind of max thermal temperature, because that keeps the PV happy, and that balance of heat energy collected goes well to satisfy basic domestic hot water generation temperatures.
Gotcha.
Yeah.
Are there any other protections that are needed in the system? Like, it's simple drain back, but
it's unpressurized. So when we put water up in there, those curious little trumpets on the corners, those are open to atmosphere. So there's no if this was a glycol-based system, there's no fear of that overheating, because the system is evacuated. And even in terms of stagnation, those little trumpets on the corner, they're open to atmosphere, and you get some sympathetic flow through there that takes away the high-end heat for stagnation. That would usually is of concern to all thermal collectors, but less so in this circumstance.
Got it. And the fluid in here is the same fluid that's in your thermal tank?
Yep, correct. Just water. Mm-hmm.
Just water. It's not closed loop. It's a drain back, but it is isolated loop. Okay, yeah. Got it.
All right. Back to your engineering background. In the automotive industry, you have to design things well and rugged. And so you have stress tested this for wind speeds, for breakage. Can you share a couple of those stories on how you've stress tested the panels as well as the tanks?
Yeah, when you go through certification procedures, for electrical and or thermal, there's standard test procedures. So when it's tested as a thermal element, Intertech, when they did that work, the module's got to go out and stagnate and be out in an environment for so many sun days as they collect them, sun space days, not Sundays, and then they take it up to temperature. They hit it with hot water to see if it breaks or the glazing, comes away. So there's those standard sets of test procedures. On the electrical side, they'll do a load test to simulate wind speeds and negative or positive pressure that could act onto the module, and it's loaded up in order to do that. Yeah.
Now, you've also attempted to drive over these modules with your truck. What did that end up with?
Made me smile because I was frustrated. No, you can certainly the load in you. We have some video clips that if we wanted to share those, that we can, that show that the module, it's tough. It's meant to, because the solar cells are not in intimate contact with the outer glazing. That means they got that air gap separation. That means it's a very durable module if you wanted to go and drive a truck on it, walk on it. The backside, having that expanded polypropylene foam means you can drop it, and so it's a very rugged module from the standpoint of just handling. And the size of it is meant for, because you can fit it, put it over your shoulder. It's under 50 pounds. You can take up a ladder, up a common lift. So its ability to get moved into place quickly is shown through its size, and then handling and mounting, it's a rugged element.
And finally, people in the Caribbean are often concerned about the impact of hurricanes. This setup was tested at Florida International University. Up to which wind speeds did this hold up?
Well, I think their system was limited out at 120, 130 miles per hour just by their test method, but they have a series of fans that are set up. It's a great video. It shows, Rob was speaking to the product, and Florida International University, FIAI, at the university where this wall of wind is, that's where structures are tested and noted. But in terms of loading on the module, so you can take, and we've done this in-house, and part of the certification or qualification procedures that they load it up with with lead shot bags or sandbags or your favorite ballast element in terms of pull away from that to show that it doesn't separate from the structure that it's mounted to. And then we can go up to 15 points in order to hold that. So we're now hearing.
Let's be a little clear on the wind speed. That was a FIU, and I think it went up to 160. That's all that we could do. But ours are designed for whatever locations we are at. We can go over 180 mile an hour designs with Garth.
All right, excellent. Thank you, Rob, for clarifying.
If I may point out, that one is important, especially here in Puerto Rico, because the minimum per code is 180.
Right.
So we would have to prove in the design that is a capacity.
Yeah,
correct. Same with Florida. So that's what.
Okay, awesome. Thank
All
you.
right. Excellent. So we've talked about the heat pump that is drawing energy from the ambient environment. We've talked about the PVT that is using the solar energy. I want to come to the third format of energy capture, and it has that really cool word in it, the de-superheater. Garth, doing your best impression of a sort of a non-engineer, right? How do you explain to the rest of us this principle of the de-superheater and how we can capture that energy?
Sure. In an air conditioning system, so the cold benefit that you feel coming out of the HVAC system, the cold air blowing in there, it's because there's been energy extracted and withdrawn out of that building. And in a refrigeration cycle shown before you, there's a hot side on that element. The refrigerant is quite hot, and there's a device that can be put into that hot fluid stream in order that water can then be circulated, or working fluid circulated by there, in order to extract that heat in case you do have that domestic hot water heating purposes or other thermal purposes within your building. And that device, whether it's built into the standard rooftop air conditioning unit or it's an aftermarket installed unit, that's called a desuperheater, also known as, in some systems, partial heat recovery systems. And they can be cycled on and off in the system in order to build to the thermal potential that you want in your system.
So the idea is basically, if you have a large air conditioning unit, say it's on the roof or it's next to your building or somewhere else on the property, that is cooling the inside of your buildings, and it's basically taking that extra heat and just blowing it out into the bushes, into the air. With this desuperheater, we can basically take a portion of that waste energy and turn it into hot water, basically free hot water. Is that a correct statement?
It couldn't be any more better than the word free.
All right, excellent. Of course, you have to pay for the investment of the device, but the operating cost essentially.
And I think that's a very important financial point that we make, because we look at those opportunities and people call them arbitrage. So if you still have to produce your thermal energy by putting in grid electricity or wherever your wherever your energy source is, versus free, then all of a sudden that arbitrage rate is extremely attractive to the customer.
Mm-hmm. All right. Let's take a look at if we buy into the notion that this is a great solution, that we want to lower the cost of our hot water bill, but clearly we understand some investment is necessary. Let's take a look at that aspect, so how we can fund the investment. I'm going to start with a case study here. This is an actual install at Bolongo Bay. The story as I heard it. Oh, you know what, Garth? I'm going to let you tell the story because you were actually directly involved in it. How did this opportunity come about, and what did you ultimately build at Bolongo Bay?
Yeah, so one of our business development people was doing a similar lunch and learn out to the hotel establishments in St. Thomas, and he chose the site as Bolongo Bay Beach Resort. And one of the owners, during the presentation, looked in there and says, "Oh, you're doing this. Come, let me show you something." So he took our biz development guy on the rooftop and showed him his decrepit, decaying, pressurized hot water system. I think at one time there was a solar thermal system hooked up, but basically you had tanks that really wanted to belong on the inside of a building that were on the outside, decaying. Their energy sources were from immersive electric, so 1 watt in, 1 watt of heat out. But the way that the whole system was constructed after investigating is that no one was getting a warm shower at Bolongo Bay Beach Resort. Number one complaint in there when the customers came back to check out during the night. So we did 2 things there. One, established a baseline thermal system with a heat pump, and 2, we put on our renewable PVT system. That system now has we have 1,400 gallons worth of total storage in place, and all the metrics that we talked about. They make their own RO water that's aggressive. Well, it goes through our plastic heat exchangers, not aggressive anymore. The heat pump system, that has a one-time fill of working fluid in it, so it's not going to degrade that system. So everything that we put in and resolved in at Bolongo means that you got much happier clients. In fact, Oliver, the water usage there, when we first put this in, the ownership says, by the room usage and all that is 10 gallons per room per day. It has now doubled, that amount, because people once again, can enjoy a good hot shower rather than a momentary cold one. They just get in the sand and the beach off of themselves for the day.
All right. Thank you for relaying that. I want to break down the economics a little bit, and I'm just going to use.
Just another quick question, and bear with me.
Yeah.
So in that model, you've got both the PVT as a heat source, and you've got the heat pump as a heat source, and then you've got your heat exchanger on the other side. So there's essentially 3 manifolds. Like, how many different configurations can we run in parallel, I would say, through that manifold?
In terms of thermal storage tanks, you can daisy chain as many as you see fit. Like the way that we have 2, but you could, nothing precludes you from putting 2, 3, 4 in a row in terms of thermal energy storage devices. And the way that the system at Belongo works is that, the primary, you got the PVT system, so the hot water that's stored in the tanks underneath the collector set. Incoming cold water gets preheated. It's in a recirculatory loop unto itself. And then once a client demands it, through a shower, through a spigot in their hotel room, it goes through the heat exchanger sets that are circulating through the rest of the hotel through a circulatory system through the heat pump. So we provide to that heat pump system as much thermal as is being produced out of the PVT system. But you do have your downer solar days, no solar, storm days. The PVT system, I've got no sun, so I can't produce. And so the backup or baseline system that we have with the heat pump, 1 watt in, 4 watts out, handles the rest of the load and the circulatory load as well.
Yeah, so the heat pump is the use case temperatures coming out of it, and the PVT is for the so the heat pump's an inline heat pump, but you're pulling just thermal energy out of the tank.
Yeah,
okay.
Correct.
Yeah,
as much preheated water energy, even down if you're even at just a 5 degree C delta over the incoming cold water, that useful work from the PVT system goes into the heat pump system to get upgraded. So it sees as much as the thermal system can supply, and those 20 modules are servicing a 45 room set of wings in the hotel.
Got it. Thank you.
Yeah, no problem.
All right. Thanks for explaining. I want to break down the economics a little bit in 2 use cases. So the first one is a mid-size hotel that also has a restaurant and a laundry. The investment here for the equipment, shipping, and install is $25,000. All equipment is eligible for 30% ITC tax credit in the U.S. and in the U.S. Virgin Islands. In Puerto Rico, that's a little more difficult. There are some ways of accessing it through a U.S. Partner, but let's say we're talking about U.S. and U.S. Virgin Islands. So that's a value of $7,500. Our thermal storage solution plus the controls are made in America, so they are eligible for a 10% booster. So it doesn't apply to the entire solution because our heat pump does come from China. It's a top-of-the-line heat pump, but it is not made in America. And then there's the accelerated depreciation eligibility, where you can now take the depreciation over 12 months, and that has an approximate value of another $2,500. So after tax credit and accelerated depreciation, the financial impact is $13,000. Then we look at what we discussed earlier. Over the life cycle of the equipment, you're not going to have to invest in additional water boilers repeatedly and the installation of that. So even that, though that expense does not occur today, it's going to occur in the future. If we discount that back to a present value, it would be approximately a saving of $5,000, which means the net financial impact comes down to $8,000. Now we look at the annual savings through reduction in the electricity usage, the avoidance of peak charges and demand charges, and reduced hot water related cost. And that's about $3,000 per year. So in this example, we have a payback period of 2.7 years against that net financial impact. In a second use case, a much larger setup here, apartment building in New York, a bigger system, $120,000 investment cost. Again, eligibility for ITC, Made in America booster, accelerated depreciation. But now in some markets, we have additional benefits. We have state and local incentives. And in New York,
Oliver,
yes,
Carla has a question.
yes, please.
Sorry, I was on mute. Thank you for that. I just wanted to ask, because you mentioned in Puerto Rico, the ITC taxes aren't necessarily that attainable. However, and this might just be like better for to add to the presentation if you wanted to. The one good thing that we do have is that Puerto Rico sales tax is extremely high. It's 11.5%. But renewables, renewable equipment, renewable energy equipment does not pay the import taxes when it comes to Puerto Rico. So it does require some certifications. I wonder if you guys have those certifications to make sure that we're not paying on those import taxes when we bring it here.
Thank you, Carla, for pointing that out. I'm not going to go on record right now to say we have or we have not, but we will definitely work on that to make sure, and we will reflect it in our presentation going forward.
Awesome. Thank you. And if you need help with that, just let me know. I've done it a couple times.
Wonderful. Thank you. So second example, now in New York specifically, there's a local law that forces every building owner to electrify, to decarbonize, as they call it. They don't want to burn natural gas or oil anymore. And if a building owner does not do that, they receive, starting in different tranches, and then with increasing intensity, they receive penalties. So building owners are trying to get ahead of that curve and avoid those penalties by moving to electric sources of building heat and electric sources of hot water, air conditioning, and so forth. So avoiding these steep penalties has an additional present value of approximately $20,000 in this example. So our cost after credit depreciation and these other incentives is down to $25,000 already. So now we have the longevity of the equipment, and in this case, it's a much larger system, and the replacement investment that would have been necessary for water boilers or individual unit heaters would have been much more significant. So we have a present value of about $20,000. And you can see here your net financial impact is almost down to zero. So if you are in the right market, in New York, they call that the stack. And there are many people specialized in identifying all the elements you can add into your stack. Your 1 year savings exceed, in this particular example, the net financial impact of your investment. Not everybody is as lucky as New York, but we are learning about all of these incentive layers and doing our best job of bringing that information to our clients. There are some incremental benefits in certain location, grid independence. If you have the PVT on the roof, your hot water component of your energy system is grid independent. If you have the heat pump alone, you still need input electricity, but if you have the heat pump combined with the PVT, again, the PVT can generate enough power to run the heat pump. And that matters, because if your grid goes down, usually you have to turn on your backup generator, and that's a very expensive source of making electricity. So in those scenarios, your savings are even higher than being on utility electricity. So who are the people behind it? Obviously, you've heard Garth giving all these great explanations here. I think by way of having done that, Garth, we've learned about you, we've learned about your background. But a second key player here is Rob. Rob spoke earlier to the 180 mile wind speeds. Rob is a very successful entrepreneur in Florida in many fields, and he is our primary investor. There's a third element we want to talk about, and that is how you can use this now to reimagine your building energy management. So beyond thinking just beyond the system as a standalone component, it can become an element of a building energy system. So here you see the familiar parts on the right-hand side, the heat pump, putting the heat into the tank, and then the water coming into the tank, picking up the energy through the heat exchanger. But then it goes into the existing water boiler. And so whenever we see an existing infrastructure, obviously if it is blown up, like in the example I gave earlier, that has to be replaced, and you could avoid replacing it by putting in our system. But if the infrastructure is still in good working condition, you can leave it in place. And what happens here is that our system essentially preheats the water, and that makes the load for the water boiler much smaller. It only has to top it off to the targeted desired temperature. It does not have to run as often. In some cases, it may not have to run at all, but there's not necessarily a need to blow it out. If a building owner wants to have that water boiler in place as a backup, they can now design it. They can reduce the scale. So not only can you save on the ongoing operating expenses, but you can also scale back your system requirements and put in a smaller water heater because you have that preheating and thermal storage capacity. The same thing works with indirect hot water heaters. In this example here in the illustration, the indirect hot water heater is actually the source of energy, so it's not a heat pump. You could have another scenario where it sits just where the water boiler was sitting. Here, you're not getting the coefficient of power benefit of having the heat pump provide the energy, but you can still charge up the thermal tank during low peak energy times and then use the energy during the times that it is needed. So at least you get that benefit. We always want to work with the client's existing infrastructure. We've seen existing solar water heaters that were still functional that we are able to integrate. So that is a great asset. To determine if this is right for you, there's a couple of questions we always ask or that you can ask yourself. The first question is, how much hot water do you currently consume? And surprisingly, a lot of our clients or people we talk to do not necessarily know that, because your utility bill doesn't break it out. You get a utility bill for electricity, one for gas, and one for water. But you have to sort of figure out how much electricity or gas is used to heat a portion of that water to the hot water consumption. So we have some proxies. Here's an example of guests in a hotel. You can calculate based on room count, average occupancy of the room, average occupancy through the season, or if we want to be on the safe side, we just take the peak season so that we design the system for the times of the greatest need. And then average gallons per day per guest. So you get to 570 gallons per day. Our system has to be configured to that need. Here's an example of a laundry. The hotel may have a laundry, or it may be a standalone laundry. We've done laundry facilities in hospitals. There's a similar logic: number of washers, how often do you use them, pounds per load, how much laundry can you fit in? And then there's, again, a standard of 2 gallons of hot water, so you can calculate that, and laundries are hot water guzzlers. We've had one client who's washing with cold water, and they are really regretting it. The staff is constantly complaining. They have to rewash, they have to spot treat. So they're moving to a hot water solution. And then the second big question is, how much do you pay for the energy to heat the water? You have your utility bills. Sometimes it's not intuitive. There is the rate you're being charged per kilowatt hour. Then there are the hidden charges. There are peak charges, there are demand charges, so we can help you look at your utility bills and get the average rate. Some people are running diesel or propane generators to make their own electricity. We can help you calculate the cost through that to really answer the question, what is the true cost of heating your water today? And as Garth described earlier, we also have a tool to actually measure. This is called a BlueBot. It clips onto the hot water line. We have to enter some information. We ensure that it has connectivity either through one of our modems or Starlink systems or by connecting to your Wi-Fi system. And then we can monitor over a day, over a week to get some reliable readings on hot water usage and then relate it back to how many loads were washed or how many guests were in the hotel at the time to validate that information. We do have some technical specs here, and Garth, maybe what you could point out is the different tank sizes that we have here. And you mentioned earlier daisy chaining them or combining multiple tanks. Can you speak a little bit to, when is a small tank needed, when is a large tank needed, and how does it even work that you could put two tanks behind each other and have that act like one system?
Okay, thank you, Oliver. So sizing wise, yeah, it's going to come down to what your system demands for energy. So we have tank sizes from 350 to, through to 700. We build 350, 500, 700 gallon. And as discussed and as shown in the lower left, we can link those up so that you can take 700, you can make 1,400 gallon, quite easy. It's just a siphon tube that connects the tanks up. Also, that goes into the tank calculation as a heat exchanger, so we can design that load side heat exchanger, whether you're on a circulatory system or whether this is a single pass system where you're taking cold water and instantly it's out to a device. We can design those systems to help you satisfy your thermal needs.
So sometimes clients ask if the tanks can go onto the roof, and they are obviously then most interested on how heavy are these things when they are full of water, and can my roof bear that load? How do you typically sort of evaluate whether the tank can actually go up on the roof?
But that's going to be to the up to the engineer that owns the roof design and the structure. In the Caribbean, let's say at the case at Belongo Bay, they got an 8-foot slab roof. There's no question on its capabilities to withstand the weight of 350 gallon tanks. Each one of those looks like a small car in terms of weight. It's a little over 3,000 pounds per, but the roof design says I'm willing. If they don't want to be on the roof, the structural engineer, the roof engineer says not going to belong there, not going to belong underneath the collectors. They can be sited, in interior of the building or to the ground. And in some circumstances, we've even, put those tanks, we've buried them at grade in order to satisfy the customer requirements.
So now if we had the tall tank and we tried to get that into a building, obviously, at some point, if you have a low ceiling, it's going to be difficult to put anything into the tank, right? To open it. What's your estimate on how high does a room ceiling have to be that this large tank could still be installed and properly commissioned?
Yeah, so the 700 gallon tank, it's 7 feet 4 inches, and we only need a 9-foot ceiling in order to maneuver in the rest of the elements at the top, which would be the heat exchanger set in order to load it in and or to make plumbing connections. So your kind of minimum roof, you got, give yourself 20 inches from the top of the tank so that you can maneuver in and do plumbing and other necessary connections.
All right, excellent. We have some time left for questions. Does anybody have any questions they would like to ask?
Go ahead.
There you go. Honestly, this is a great presentation. I'm really happy that I was able to make it. and learn a little bit more about how the system works. And when I was looking at the pre-design that we worked on, I was wondering, like, how is it possible that we have so little amount of panels? But now I understand this is an incredibly efficient system. My question is, would we since we are applying for the Puerto Rico Tourism Company tax decree, there's a lot of questions that they're going to be asking us in regards to the design, because they want to make sure there's not a lot of greenwashing. Now, even though for me this is pretty obvious about how it is like very renewable, and especially when we are the way we are doing it with capturing rainwater to produce our water through the system, can we use this presentation or maybe a summarized version of this presentation to send to the tourism company along with our application?
Absolutely. If you tell me what the questions are that they are asking, I can put together a custom presentation for you that addresses each one of those questions with the necessary information.
Okay. I don't think custom might be 100% necessary. I think it's pretty basic in regards to, like, they just want to see like how things work, what materials are recycled. So for example, that part where you were saying that the it's talking about the life cycle after, if the hotel ever gets like demolished or something like that, what happens to these materials? That's something that's like super powerful in regards to the application. But if we do need to add something specific, I'll let you know.
Yeah, I will definitely send you this as a PDF, and then you have that in your hands.
Awesome. Thank you.
You're welcome. Any other questions? All right.
Hey,
well,
hey,
yes.
on those two questions, on the related to the PVT, we've got a constant slope, right? We don't have multiple slope configurations.
You can, down in the lower latitudes, Puerto Rico, 20 degrees. So we design the racking. If you're up in our kind of latitude here in the Midwest, we're going to be at 40, 45 degrees. And those racks are adjustable the way that we manufacture them. You got, 5 or 10 degrees worth of play either way to satisfy your, the pitch that you tend to want to achieve. In the lower latitude ones, they're 4 or 5 degrees adjustment either way, but we usually pitch them in, for Puerto Rico, St. Thomas, 20 degrees, and up here 45.
Okay, that's great. And then the stringing and the inverter on the electrical side is that's just so you look at the thermal load, your sizes on the thermal load, you got your standard configuration, and then are they all strung together, right?
Yeah, we use microinverters. So one from which services out 4 of our modules. The modules are rather small in size, and so a microinverter usually would serve out 2 modules. It serves out 4, and so we supply all the cabling for the for that, and then mount those inverters on the side of the array structure.
Is there so we are using micro? I don't need a rapid shutdown.
Yeah, they're contained within. Yeah, so that whatever that specification are for a rapid shutdown, that's contained within that. We use an AP systems unit.
Okay, and that's all integrated.
Correct. But we do, on the rack, we'll have a master shutdown, manual shutdown, but it doesn't have to be electronically connected.
I got you. That rack that I'm looking at on the screen there right now, is that what the rack would look like for the 180 wind? Surely there'd be like a diagonal cross brace in there.
Yeah. There's more, like the one if you went up on Belongo Bay Beach Resort, we tie right onto the rooftop, and there's more structural elements, and plus the array is only canted at 20 degrees up from there. What we do, we fully tie into the roof. You probably have onto that concrete roof 5, 10, probably 50 penetrations in order to hold the rack array structure in place.
That's me. Those are my questions.
All right, excellent. Great. Well, thank you all again for giving us your time and appreciate it. I will send the PDF version of this presentation to all participants. And if you have any friends, colleagues, business partners who might be interested, please send them our way. We continue to have these seminars every Wednesday, every other Wednesday, alternating in time between noon and 2 o'clock Eastern time. Thank you, and we'll hope to talk to you soon. Thank you. Bye-bye.
Everybody.